Welcome back to this next video in which we are discussing field extensions. In this video, what we're now going to turn our attention to is starting with a field, okay, and we'll call that field capital F here. We will take some irreducible polynomial in the ring of polynomials over this field, okay. That polynomial will not have a root in the field. Okay, we'll also have to insist that it's greater or equal to degree 2, I'll explain that in a moment. It will not have a root in the field, because of course if it did have a root in the field then it would have a degree 1 factor, and therefore it wouldn't be irreducible. And what we're going to do is build a larger field, a field extension of our field capital F, which will have a root to that polynomial. Okay, so let's go. This is a really important concept. This is, again, field extensions are the centerpiece of all the field theory, and this is the basis for studying field extensions, talking about actually building field extensions, and that's what we're going to now do. Okay, so we're going to start off with some field capital F. Okay, this is our starting field, and we're now going to consider some polynomial p of x here, which is in the ring of polynomials where the coefficients are from the field capital F. Okay, so it's in f adjoin x here. Now, we're going to want this polynomial to be irreducible. Okay, so this is going to need to be irreducible in order for this to work. Now remember what irreducible means. Irreducible means that any product that you can come up with that makes this polynomial. Okay, so irreducible in the ring of polynomials, f adjoin x here, means that any product that you can come up with, and I'll write this out. So if you can write p of x as a product, let's say a of x times b of x here, then one of the two things that is multiplied here together to give you p of x is going to be a unit. Okay, and that's true for all all products that make this polynomial p of x if it's irreducible. So it is not possible, if the polynomial is irreducible, to find a product which makes that polynomial in the ring of polynomials f adjoin x here, such that neither of these two polynomials is a unit. Whenever you find a product that makes this polynomial p of x, which is we are assuming here irreducible, then one of them will be a unit and the other will just be an associate of that original polynomial that you're trying to make. Okay, so they're all boring products that make this polynomial. Okay, so we're going to assume it's an irreducible polynomial. The other part of the definition of irreducible is that you can't apply the definitions of irreducible and reducible to the zero element, okay, the zero polynomial in this case, or the units, which in this case are the constant polynomials. Okay, so to even apply the definition of reducible and irreducible, you are only applying it to the non-constant polynomials. So the instant I'm saying it's irreducible, you can assume that it's a non-constant polynomial. I'm also going to assume that our polynomial is not degree 1. Now all of the degree 1 polynomials are going to be irreducible in the ring of polynomials over the field capital F, because the field is an integral domain. Okay, so you can only find products that are going to be a constant polynomial times another degree 1 polynomial that will make a degree 1 polynomial, and of course a constant polynomial is a unit. Okay, so all degree 1 polynomials are irreducible, but I don't want you to pick a degree 1 polynomial. Okay, so we're going to assume that the degree of the polynomial p of x here is greater than or equal to 2. And the reason I don't want you to pick a degree 1 polynomial is that if you pick a degree 1 polynomial, all of the degree 1 polynomials already have roots in the field capital F. Okay, they all have roots. So if I give you an example, if we take the degree 1 polynomial a0 plus a1 x here, where a0 and a1 are just elements of the field, then if you evaluate this polynomial at the element, what should we have? We'll need negative a0 multiplied by the multiplicative inverse of a1, usually written like so. Okay, so if you consider evaluating this polynomial from the ring of polynomials over your field at this element, then of course you will find that the answer is 0, because of course the multiplicative inverse of a1 will just cancel with the a1 here, and then a0 will cancel with the additive inverse of a0. Okay, so all degree 1 polynomials do have a root in the field capital F, so we're not going to consider those either. So we'll do degree 2 polynomials. Okay, so you've got some irreducible degree 2 polynomial, and now that allows us to conclude that this polynomial cannot have any roots. Okay, no element in the field that you can possibly come up with will be a root for this polynomial when you use the evaluation homomorphism for that element on the ring of polynomials over the field. Okay, and the reason I can conclude that is that if there was a root of this polynomial, then we know, we've studied in the playlist on ring theory, specifically in the video on factorization of polynomials over a field, that if a polynomial has a root in your field, then it will have a degree 1 factor, and therefore it will be reducible, basically. It will be writable as a degree 1 polynomial times a polynomial of degree 1 less than the original polynomial. Okay, so it won't be irreducible. So from these conditions then, we can now conclude that our polynomial has no roots. Okay, and again, I'll stress that we need the degree of the polynomial to be greater than or equal to 2 for that to be true, because all the degree 1 polynomials are irreducible, but they do have roots. Okay, so it's only true if we talk about degree 2 polynomials or higher that they're going to have no roots if they're irreducible. Okay, right. And now what we're going to consider doing is trying to build a field extension of the field capital F, a bigger field that contains the field capital F, and which is going to have a solution to this polynomial P of x, which therefore is no longer going to be irreducible in the ring of polynomials over our larger field extension. Okay, so here comes the big claim. Okay, so here comes the big claim. What you can do to construct this then is take the ring of polynomials over the field capital F and quotient it out by the principal ideal generated by P of x here. Okay, so you'll take the ring of polynomials over the field capital F, okay, and you'll quotient it out now by the principal ideal, and this is a quotient now, the principal ideal generated by the polynomial P of x, okay, which will be a principal ideal in the ring of polynomials over your field capital F here. And the claim is that this is a field extension of F, so that I'll write down, okay, this is going to be, we'll call it K, okay, so we'll call this structure K, and the claim is that K is going to be a field extension over F, and moreover, it's going to have a root to the polynomial P of x, so it will have a root with a root to the polynomial P of x to P of x. So there is some element in the in this new field extension here, which, when we apply the evaluation homomorphism to this polynomial P of x, will give us 0. Okay, now the first thing I should explain is that this polynomial P of x will still make sense as a ring of polynomials, as a polynomial in the ring of polynomials over the field extension K, because of course all of its coefficients are from the field capital F here, okay, and F is a subfield of the field extension capital K, so P of x will therefore still be in the ring of polynomials over the field extension K, basically. Okay, so it will still be relevant to talk about having roots to this polynomial in the larger field extension capital K because of the fact that it's a field extension of the smaller field capital F, and we'll see this more later. Okay, so this is the great claim that you can always construct a larger field. You can always construct a field extension such that you're now going to have a root to your polynomial P of x, which previously had no roots in your initial field capital F. Okay, so let's now understand how this actually works. Okay, so the first thing then that I want to show you is that if this polynomial P of x is irreducible in the ring of polynomials over the field capital F, then the principal ideal generated by it will be a maximal ideal, and therefore when we perform this quotient ring here, we will actually end up with a field. So that's the first really important thing to show, that this quotient ring structure that we're getting here is actually going to be a field, and the way of doing that is by proving that the ideal that you're quotienting out by is a maximal ideal. We prove in the video on maximal ideals in the playlist on ring theory that whenever you quotient out by a maximal ideal, you do indeed end up with a field. Okay, right, so let's prove that. I will go over that proof, although we have talked about it in earlier videos in the playlist on ring theory, but I'll repeat that here because that's really central. Okay, so the first thing I want to show you then is that the principal ideal generated by this polynomial P of x is maximal, and the reason is that the polynomial p of x is irreducible in the ring of polynomials over the field capital F, and the ring of polynomials over the field capital F is a principal ideal domain. Okay, so how are we going to prove this then? So to prove that a ideal here is a maximal ideal, what you need to show is that if you have any other ideal that is in between it, and I'll write this like so. So if we've got our principal ideal generated by p of x here, let's suppose that we have some ideal that's in between it and the unit ideal, which is the entire field capital, well, the entire ring, sorry, the entire ring of polynomials over the field capital F. Okay, now because this is a principal ideal domain, remember all rings of polynomials over fields are Euclidean domains, and all Euclidean domains are principal ideal domains. Okay, so because this is a principal ideal domain, all ideals of this are going to be principal ideals, so it will be a principal ideal generated by some polynomial which I'll call m of x here. Okay, so I'm going to assume that we have some ideal here which has to be a principal ideal because it's a principal ideal domain, and that's absolutely crucial to be able to conclude that this is maximal, that this has to be a principal ideal here generated by some polynomial there. We're going to assume we've got this ideal that's in between these two, so it completely contains the ideal generated by p of x here, and it itself is contained within the ring of polynomials over the field capital F, the unit ideal. And what we're going to show is that it is not properly in between the two. Okay, so we're going to show that either it is equal to the ideal generated by p of x here, or it's equal to this unit ideal here, the entire ring. Okay, it's not actually properly in between the two. It doesn't properly, either it doesn't properly contain the principal ideal generated by p of x, or it's not properly contained within the ring of polynomials over the field capital F. So it's not properly in between the two. And if we can show that there can exist no ideal that is properly in between the two, then that of course shows that this ideal here generated by p of x is indeed maximal. That's the definition of maximal, that you are maximal with respect to proper ideals. There is no larger proper ideal that properly contains you, okay, in the ring. Right, so let's show that then. So it's a very, very easy argument, and we're going to now use the fact that this polynomial p of x is irreducible. So I feel like we should try and squeeze it in here, okay, since we've got this picture drawn here. Okay, so basically, because the entire principal ideal generated by p of x is contained within this ideal generated by m of x, that means in particular that the polynomial p of x is going to have to be contained within this principal ideal generated by m of x. Now all things in the principal ideal generated by m of x are just multiples of m of x, so that means that p of x is going to be some polynomial which I'll just arbitrarily call q of x here, times m of x, okay? Otherwise p of x wouldn't be in the principal ideal generated by m of x, and therefore the principal ideal generated by p of x wouldn't be contained within the principal ideal generated by m of x. Okay, so now I have this line here. Okay, that's just from this contained in symbol here. Right, now we apply the fact that the polynomial p of x is irreducible in the ring of polynomials over the field capital F. What does that tell us? One of these two things has to be a unit, i.e. it has to be a constant polynomial. If m of x here is the unit, then of course the principal ideal generated by m of x is going to be the entire ring of polynomials f adjoin x here. Okay, if you generate the principal ideal of a unit, you get the unit ideal. Okay, so that would be this arrow here. So if m of x is the unit in this expression, you can conclude that the principal ideal generated by m of x is equal to the entire unit ideal. If, on the other hand, q of x is the unit and m of x isn't a unit, then what you can conclude is that q of x is a constant polynomial, and therefore what will exist is a multiplicative inverse for q of x. Okay, so we might as well just call q of x q now rather than q of x, because it is just a constant polynomial. It will have a multiplicative inverse in the field capital F, because of course it's not going to be 0 here. Okay, we're assuming p of x is a non-zero polynomial. Okay, I should probably have stressed that at some point. It's a non-zero polynomial. I suppose it's swallowed into the definition of irreducible, because you wouldn't be able to say it was irreducible unless it was a non-zero polynomial. Okay, but because because we know this is a non-zero polynomial, q of x cannot be 0, or rather q cannot be 0 here. Okay, so it is going to be some non-zero constant, and therefore we can multiply both sides by its multiplicative inverse, and then we get this expression, 1 over q times p of x is equal to m of x. Now what does that tell us? That tells us that a multiple of p of x in the ring of polynomials over the field gives us the polynomial m of x. Okay, that tells us in particular that m of x is contained within the principal ideal generated by p of x. Okay, because look, here it is, a multiple of p of x. So m of x is contained within the principal ideal generated by p of x here. Okay, now the instant a polynomial is in an ideal, then all multiples of that polynomial have to be in the ideal. That goes for an arbitrary ideal in an arbitrary ring. Once you've got an element in an ideal, all multiples of it have to be in there, just by definition of an ideal, because it has to be closed under multiplication. So what we're then able to conclude is that the principal ideal generated by m of x is completely contained within the principal ideal generated by p of x. This statement along with this statement then shows that this one is actually equal to the principal ideal generated by p of x. Okay, so if q of x is the unit, then you can conclude this arrow here. Okay, so end of proof. We've done it. Quod erat demonstrandum. Okay, this polynomial being irreducible, and because we are working in a principal ideal domain, that's incredibly important. The fact that we were able to conclude that this ideal that was in between them was generated by a single polynomial here, that was very important. Without that, you wouldn't have been able to complete this argument. Okay? So the fact that this is an irreducible element and the fact that we're working in the principal ideal domain shows us that the principal ideal generated by this polynomial p of x is maximal. Hence, when we quotient out our ring of polynomials f adjoin x here by the principal ideal generated by p of x, we are going to get a field, and we're calling that field capital K. Excellent, we've done this quotienting out, we get a field capital K. The next question is, brilliant, we've got a field, how on earth do we actually know that this is a field extension of the field capital F? Okay, we need to show that F is a subfield of this, or rather that this is a field extension of F. So what we need to find is a very natural injective homomorphism of the field F into here, an inclusion map that shows how F is contained within here, and then of course we will be able to actually think of this as being a field extension of our field capital F. Okay, so let's now do that. So how then am I going to find my injective homomorphism from the field capital F into this quotient ring of the ring of polynomials over F, quotiented out by the principal ideal generated by p of x? Okay, well, what I'm going to use is the fact that there exists a homomorphism from the ring of polynomials over F into the quotient ring. Okay, or what we now know is actually a field, the field K. Okay, so we know there will exist a very natural homomorphism from the ring of polynomials over the field F into the quotient ring. Okay, so the ring of polynomials over F quotiented out by the principal ideal generated by p of x. Okay, that is assured to us by the first isomorphism theorem of rings. Okay, you can always map the ring that you're quotienting out quotienting out by some ideal for onto the quotient ring. Okay, and the way that this mapping will work is if I draw a little picture here. So let's say that this is the ring of polynomials with coefficients in the field capital F. Okay, so this is my f adjoin x here, and I'll just outline it in pink here. So this is f adjoin x, and then of course when I construct this quotient ring of f adjoin x quotiented out by the principal ideal generated by p of x, what I'm going to do is I'm going to take the principal ideal generated by p of x, which of course will just be all other polynomials in the ring of polynomials over the field multiplied by p of x, the set that contains all of those multiples. Okay, so it's going to be a subset of the ring of polynomials over the field capital F. Of course, when I quotient out by that, what I'll be doing is dividing up the ring of polynomials over the field capital F into the additive cosets of my ideal here. Okay, and those additive cosets will now become the elements of my quotient ring, and addition will work by taking representatives of the cosets, adding them together in the initial ring of polynomials over the field, and then taking the coset that contains the answer, and the same for multiplication. Okay, and we've now shown that that is going to be a field. Now, the way that this homomorphism will work then is it just sends any polynomial in the original ring of polynomials over the field capital F onto the coset that contains it. Okay, so remember the elements here are the whole cosets. So you'll just send any polynomial onto the coset that contains it. Okay, so that's what you're doing here. Right, and we know that that is going to be a ring homomorphism. It's the very natural ring homomorphism that you can always say. Okay, so for an arbitrary ring, you can always say that there is a very natural ring homomorphism from the ring into the quotient ring R out by an ideal, where you just map all of the elements onto the cosets of the quotient ring here, okay, that contain them. I hope that's very intuitive to you, because of course addition and multiplication are going to be compatible in this way because of the way that we define addition of the cosets by taking representatives and adding or multiplying them together in the initial ring, and then taking the coset that contains the answer. Okay, so we're just using that fact here. So there's a very natural ring homomorphism, so addition will be compatible between the two, multiplication will be compatible between the two, and the multiplicative identity here will be mapped onto the multiplicative identity over here. Okay, so that's all very well and nice, but we don't want a homomorphism from the ring of polynomials over the field capital F into our quotient ring here. We want a homomorphism from the field capital F into here. But of course the field capital F is a sub-portion of this. It's a subfield of this ring of polynomials over the field capital F. It's a subset of it that, with the restricted addition and multiplication laws on it, obeys the axioms of a field. So what I'm now going to do is restrict this homomorphism pi down to F, and the way people write this is pi and then they put a line, a vertical line like so, and then subscript it F, and this just means pi, the mapping pi, restricted to the field capital F. Now the field is a subset, a very natural subset of the ring of polynomials f adjoin x, because all the constant polynomials are effectively the field contained within this larger ring. Okay, so this isn't a field extension though, because it's not a field, it's a ring. Okay, but you can still talk about this being a subfield of that. Right, so we're going to now restrict our mapping pi to the field capital F, and it's going to work the exact same way. You're just going to map all of the constant polynomials, all of the elements of F, onto the coset in this quotient ring that contains them. Okay, so it's going to be a mapping from F adjoin X, from F to this quotient ring, the ring of polynomials over the field capital F, quotiented out by the principal ideal generated by this polynomial p of x here. Okay, now, the first thing then that I need to argue is that this is still a ring homomorphism. Now, why is it still a ring homomorphism? Well, because addition is still going to be compatible between the two. Okay, if addition and multiplication for that matter is also going to be compatible between the two, because think about it, if addition and multiplication were not compatible between the two, then they wouldn't have been compatible between the two over here, because this is just a sub-portion of the domain of this map up here. Okay, so if it wasn't the case that addition and multiplication were compatible in this restricted version of this map, then it wouldn't have been compatible in the larger map over here, and therefore this wouldn't have been a ring homomorphism. Okay, so addition and multiplication are going to have to be compatible in this one, and also the multiplicative identity is going to still have to go into the multiplicative identity, again, because otherwise this is just a restriction of this. If it isn't true that the multiplicative identity here goes on to the multiplicative identity here, then it wouldn't be true over here that it went on to the multiplicative identity here. So just because it's a restriction of this one means that it is instantly a ring homomorphism, and indeed that's true in arbitrary ring theory. If you take a subring of this ring capital R, it doesn't need to be a subfield, it just needs to be a subring, and restrict the mapping down to the subring, then it's still going to be a ring homomorphism. It's not necessarily, in fact it's not at all, going to be a surjective homomorphism anymore. This was a surjective map. Okay, this is only going to go on to a subset of this now, but it is still a ring homomorphism. Okay, right, so excellent. We've now got our restricted ring homomorphism, and excellent, this is a map from the field capital F onto the coset that contain these constant polynomials. So any constant polynomial is just going to be mapped onto the coset that contains it. So writing this out explicitly, this mapping pi restricted to F is just going to map any element, and I won't call it X, okay, because that's the indeterminate we're using here. What should I call it? I'll just call it little a. Okay, little a is some element of the field, and it's going to be mapped onto the coset that contains it. So a is just a constant polynomial, and it will just be mapped onto the coset that contains it, and the notation we'll use for the coset that contains a is just going to be a bar. So if a is the constant here, then we call this coset that contains a bar. Okay, so we've got a ring homomorphism. For this to be an inclusion mapping, we need it to be an injective ring homomorphism. We don't need it to be surjective, but we do need it to be injective. Okay, we don't want loads of elements of the field being mapped onto the same coset, otherwise that's no good as an inclusion mapping. We want every single element of the field to go onto a separate coset so that we can truly say that, look, there's a copy of your field capital F inside this new field, which is the quotient ring of the ring of polynomials F adjoin X, quotiented out by the principal ideal generated by P of X. Okay, so how then can we show that this is an injective ring homomorphism? Okay, well this is a rather nifty argument. This is a ring homomorphism, so what do we know? The kernel of it must be an ideal in the domain here. But this is a field, and fields only have two ideals. They have the zero ideal and they have the unit ideal. The zero ideal is the ideal generated by 0, it just contains the element 0. The unit ideal is the ideal generated by 1, it contains the entire field. Those are the only two ideals that can possibly exist in a field. Okay? So that means that the kernel of the ring homomorphism has to be one of these. Now, if the kernel of the ring homomorphism here was the unit ideal, then that would mean that the entire field was mapped onto the additive identity over here, 0 in here. But what is 0 in here? 0 in here is the ideal the ideal generated by P of X here. Okay, because this principal ideal generated by P of X, this will contain 0, which will be 0 times P of X. So it will contain 0. So this is the coset that contains 0, which we could call 0 bar, and this will become the additive identity in the quotient ring here. Okay, now is it going to be true that all elements of the field, all the constant polynomials are going to be in here? Well, I hope it's obvious that that's not going to be true, because for instance 1 is a constant polynomial. Is 1 going to be in here? Is 1 going to be some polynomial times P of X? Is 1 going to be of the form, what should I call it, A of X times P of X? Oops, I've called it Q of X times P of X. That's a mess now. Okay, so this is the polynomial P of X here. Okay, well of course it's not. You can't get this to go down in degree by multiplying it by a polynomial. Okay, the only exception to that is that you can make it equal 0 by multiplying by 0, but when you multiply it by any other polynomial apart from the 0 polynomial, the degree of this thing is only going to stay the same or get bigger, so you can't get it to go down to 1. Okay, so 1 is not going to be in this principal ideal generated by P of X, so it's not going to be being mapped onto the additive identity, the 0 element in the quotient ring. Okay, so that means that the kernel of this ring homomorphism here cannot be the unit ideal, but that leaves us only one option, it's the 0 ideal. And when the kernel of a ring homomorphism is the 0 ideal, that, by the first isomorphism theorem of rings, shows us that this ring homomorphism is indeed injective. That's proof enough for us to now conclude that this ring homomorphism is injective. Okay, now injective ring homomorphisms are very nice because although they're not bijective, they can be made bijective, okay, by making them surjective. So all we now need to do is try and think about making this surjective, and the way we can make this surjective is just thinking about the subset, which will in fact be a sub-ring, in this case an actual subfield, of the quotient ring here, which is the image of this homomorphism. So we can think about the image of the ring homomorphism of pi restricted down to F. Okay, so this is just all the elements over here that are actually being mapped onto by from the field capital F by this ring homomorphism pi restricted down to F. Okay, now if we were to restrict this ring homomorphism down and just think about the codomain being this, okay, we can get rid of the rest of the codomain because it's not involved in this restricted ring homomorphism at all. So if you were to restrict down your attention just to the image of pi restricted to F here, then of course this map would now be an injective surjective ring homomorphism, and such a ring homomorphism is obviously an isomorphism. Okay, so in fact the field capital F is going to be isomorphic, and I'll write isomorphic like so. One squiggle there with two equals is underneath. There's loads of different notations for isomorphic. Some people write it like that, two squiggles. Some people write it one squiggle with a straight line underneath. Some people write it one squiggle with two straight lines underneath. They all mean exactly the same. They all mean isomorphic too. Okay, different authors prefer different ones. I'm in the mood for this one here where we've got one squiggle and two straight lines underneath it. Okay, the image of this restricted ring homomorphism pi restricted down to F is going to be isomorphic to the field capital F. That's why injective ring homomorphisms are always so lovely, because you can think of them as an isomorphism onto a subset of the codomain here. Okay, because the image of pi restricted down to F will of course just be a subset, in fact a subfield because it's isomorphic to a field here, okay, a subset of the quotient ring F adjoin X quotiented out by the principal ideal generated by P of X here. Okay, right, so that's absolutely lovely, because now what I have shown is that there is an isomorphic copy of this field capital F in our quotient ring, which we know of course is a field. So there's an isomorphic copy of the field capital F in your new field capital K. So you can now say effectively that F is indeed a subfield of capital K. I know this isn't the symbol for subfield, there isn't really a unanimous symbol for subfield, but it's the best I can do, writing F as a subset of K. Okay, so there is a very natural way then of thinking about the field capital F as being contained within our new larger field capital K, okay, which is just this mapping which takes all of the constant polynomials onto the cosets that they are contained within, and now what I've shown you is that all of the constant polynomials are going to be in separate cosets in this quotient ring. Okay? So there's a very natural way of thinking about your initial field capital F as being contained within the larger field capital K. So we can now think of capital K truly as being a field extension of capital F. Okay, so this is all looking good. The final thing then that I want to show you is that indeed it will actually have a solution to the original polynomial that we wanted to create a solution for. Okay, so the first thing I need to argue is that my polynomial P of X is still going to be validly thought of as a polynomial in the ring of polynomials over K. Okay, and that's of course going to be true because F is a subfield of the field extension capital K. So this will be the set of all polynomials where the coefficients are in the field extension capital K, but of course this polynomial has coefficients in the field capital F, but they're now still in K. So this is absolutely fine to view this now as a polynomial that is in the ring of polynomials over the field extension capital K. Okay, now what we can consider is, are there any roots for this polynomial in our new larger field, capital K here? Okay, is there any element that if we apply the evaluation homomorphism to this ring of polynomials over the field capital K that gives us, when applied to this polynomial P of X, will give us 0 in the field capital K? Okay, and the answer is yes. Let's now think about the coset that contains the element X. We haven't previously thought about this. Okay, so far all we've thought about is the cosets that contain the constant polynomials. Okay, now let's think about the coset that contains the polynomial X. Now this is a very basic polynomial, but it is a polynomial in the original ring of polynomials over the field capital F. Okay, so the polynomial which just has 1 in front of x to the power of 1 and 0 in front of all the other powers of x, that is going to be a polynomial in the ring of polynomials over the field capital F. It's going to end up in some coset over here, so let's put that here. Here is x, and then we'll have a coset which we'll call x bar here. Okay? Right, and now let's consider what will happen if we evaluate this polynomial p of x, which is in the ring of polynomials over the field capital K, with the element x bar here. So let's now consider p of x bar, the evaluation homomorphism for x bar applied to p of x. Okay, that's rigorously what this is, but of course we'll just write this like so. Okay, now what do we have to do then here? Well, let me firstly just write out explicitly my polynomial p of x, because I haven't done that yet. So I'll write it out here. It will be p0 plus p1x plus all the way up to pn x to the n, where n is the degree of the polynomial. Okay, and all of these coefficients pi are just from the field capital F. Now remember, the addition and the multiplication in this polynomial, formally they are just symbols. Okay, formally all this is lots of powers of x, which are effectively the placeholders with coefficients from the field capital F in front of it. But the addition, really, it's just a symbol, a thing that you put in between the different powers of x. Okay, and the powers of x, again, it's just symbols, they're just placeholders. And putting the coefficient in front of the x, formally, that's just, you know, creating a symbol. It doesn't necessarily mean multiplication at all. Okay, so formally, the really formal interpretation of polynomial is that it's just a symbol of this form, where you've got elements of your field sitting in front of these powers of x, which have these strange plus symbols in between them. Okay, now when we apply the evaluation homomorphism, the meaning changes completely, because now what we do is we say, okay, now change all of the additions and the multiplications and the taking to the power of something into actually meaning something in the actual field in which you're evaluating it, okay, which in this case will be our field capital K here. Okay, so the addition is going to become addition in the field capital K. Multiplication is going to become multiplication in the field capital K. Raising to the power will mean multiply this element by that itself that many times in the field capital K. Okay, so the addition has changed meaning. So now suddenly everything's going to now mean addition and multiplication in the field capital K. So what we'll have to do is take P0 plus, okay, and then we'll have P1, and then we'll have X bar here, and it's struggling for space here, so I'll just try and squeeze it in, plus all the way up to Pn times X bar to the n here. Okay, and note, all of these additions are in the field capital K, all of the multiplications, I'll put red dots in there, are in the field capital K. Raising x bar to the power of something means multiply x bar by itself that many times in the field capital K. So everything's gone from just being a boring, rock-solid, nettle-minded symbol to now actually meaning something in the field capital K. That's what you do when you take when you evaluate a polynomial at a certain value. And we know, of course, from our work in ring theory, there is a video in the playlist on ring theory entitled The Evaluation Homomorphism, that this is indeed a ring homomorphism. Okay, right. So, now let's actually perform this. Let's try and work out what element of the field capital K will we get if we do this. And we are hoping that we're going to get 0, the additive identity in our field capital K. Okay, so how do we add and multiply in the field capital K? Well, of course, we take representatives of the cosets. Okay, and really, I should probably update this. Now, when we think of this polynomial P of x in the ring of polynomials K over x, if I'm being utterly rigorous, really we should now think of this as being the coset that contains P0, the coset that contains P1, and the coset that contains Pn. But of course those are completely analogous to the original elements of the field, because we know that this is very naturally included in our larger field capital K. So really I should put bars over this as well. Okay, so we take a representative from this we'll take representatives from all these cosets, turn the multiplication and the additions into what they were in the polynomial ring. Okay, so turn into what they were in the polynomial ring f adjoin x here. So I'll now colour code all operations in the polynomial ring in green here. Okay, so this is going to become, let's take a representative from here. We might as well take p0, we'll add it to, we'll take the representative p1 from here, we'll take the representative x from here, okay, and so on. And we'll take the representative pm. Why would we pick any other representative? We could, but why on earth would we? Okay, and now all of these operations are now additions and multiplications in the polynomial ring, and the taking to the powers are in the polynomial ring, taking x to a certain power in that polynomial ring. Okay, and of course when you do all of this you will end up with the polynomial, and now it's going back to the wooden sense of a polynomial. It will go back, when you perform these additions and multiplications in the polynomial ring, you'll end up with the polynomial that will look like this: p0 plus p1x plus all the way up to pn x to the n. Okay, now everything's gone back to being wooden. It's gone back to being a symbol in this set. Okay, here it actually meant add this polynomial, which was just the monomial x, multiply this with the constant polynomial p0, p1 here, etc. This was all operations in there, okay, with loads of little polynomials. This was a constant polynomial, this was a constant polynomial, this was a monomial, etc. Okay, it's gone from being that to now just being the symbol here, the wooden symbol, where these pluses and multiplications are just symbols, okay, and you've just got the powers of x are just placeholders with the coefficients from the field capital F here, okay, but now we've got this element in the ring of polynomials f adjoin x. What do we actually need to do to get the answer back again in the field capital K here? Well, we need to take the coset that contains this. Okay, so I really should have put a bar right over this, because you work this out and you have to take the coset that contains this. So we take the coset that contains this polynomial, and of course what coset contains that polynomial? Well, that polynomial is just p of x here. Okay, so this is going to be the coset that contains our polynomial p of x, and the coset that contains the polynomial p of x is the same as the coset that contains 0. Okay, so it's the additive identity in the larger field capital K, and there you are. There is now your proof that this element, the coset that contains the monomial x, that is now the element in your larger field capital K, which is the root to our old polynomial p of x. So I have now shown you my claim. Okay, if you have a field capital F and you have some irreducible polynomial p of x in the ring of polynomials over the field, let's say it's degree 2 or greater, because we're not really interested in adjoining on a root to a degree 1 polynomial, okay, because that's already got a root. What we can now do is create this larger field, which is a field extension of our original field capital F, and which will have a root to the polynomial p of x now, and the way that you do it is simply by taking the ring of polynomials over the field and quotienting it out in the way that we learned in ring theory by the principal ideal generated by the polynomial p of x. Okay, right, we will not end this video here, however. We will have a break, but come back, and after the break what we will do is we will explore the structure of this field extension in more detail. We have proven some interesting things about it now. We have proven it is indeed a field extension, and we've proven that it does have a root to the polynomial that we wanted it to, but we don't have much intuition yet for how addition and multiplication will work, okay, and things like that. So I want to gain more intuition about this field extension in the next video.